again. And then we start at 9:05, I guess, because I think I created I posted this particular link a bit late. Let's start at 9:05 or 9:10. Let's see how the number of participants comes in. Okay, so right now we only have 33. I think we are expecting around 100 plus, supposedly. So let's wait for a while more, okay? So in the meantime, please go and take your attendance. Today will be mainly on your non-parametric test class. Okay. After that, you have Q&A session in terms of if you still have questions on the project or the case study report. Okay. Then finally, after the classes, then I would like to ask for the group project leaders, okay, from tutorial group 1 and tutorial group 2, can you please stay back for a while so that I can ask you some questions? All right. So that will be for today's what we want to do for today. So let's wait for a little bit while more. Okay. Right. Be coming back very soon. Okay. So let's browse. Screen first. Can you see my share screen now?
Yes,
Anyone? Any idea? Anyone can see my share screen now?
Yes, Doctor, can see.
Sorry, can you say again? So I forgot I muted my mic. My micro. Yeah. So you can, right?
Yes, Doctor.
Thank you. No wonder why I can't hear any response. Okay, thank you. So it's 9:07 now. Let's see, 57 of you. As many of you are not here. Let's wait for. We start at 9:10. Okay, no matter how we start at 9:10. Sorry, 9:10. 9:10 a.m. The meantime, please check your attendance. You can take your attendance and also what else? Okay, maybe I put it over here first. We talk about this one first before we move on to the classes. Then we move on to the quickly on the tutorial part. Okay. Then in that case, week 13. I mean this Wednesday, right? Will be fully on Q&A. Just in case you have something to ask over here, then you can ask as well. But yeah. So move on here. Let's wait for another 2 minutes before we start. Okay, let's start now by beginning the recording. Okay. So it started. Okay, so the recording is started. We can now start the class. Okay. Maybe I should not start over here as well. I should start from here because we are already done all this. Okay. Quiz. It's already done. Okay. I think you can still see your online quiz and online quiz replacement is still clickable, but later on you actually see one part of it. It's still hidden because unfortunately I want to complete it next last week. Okay, but unfortunately I have some issues on accessing the spectrum. So later on, I will actually enable this one and then let you all see. You have 1 week of time to actually review the marks adjusted, okay, based on whatever that we have discussed before, including your online quiz. Question 7, every one of you will actually get 1 mark, okay, regardless you're correct or not. So there will be so-called quiz marks adjusted. Please look for this one for your final marks of quiz, okay. I'm not sure I'm able to post tonight or tomorrow, but no matter how, if it's tonight, then you can actually have the time to review it up until next Monday. Then you can actually, like, if you have any questions, you can ask me over that particular period. Same goes for the midterm test, okay? You actually see midterm test, set 2 replacement, there are a lot, and then later on you also see midterm test marks adjusted, okay? Because some of you are actually taking replacement, so I will need to combine these 2 set of marks, and fortunately, midterm test, none of you complaining to me in terms of the settings problem. So luckily, there's no bonus mark from that. Then later on, move on to group project. Group project is actually different in terms of your tutorial groups, okay? But for my tutorial groups, some of you are already presented, and also And also some of you are presented, and also haven't sent me the report yet, unfortunately. So once you send me the report, I will be able to give you carry marks, okay? Because carry marks consists of your quiz, midterm test, and also a group project. But if you don't submit your group project in terms of the report itself, I will not be able to give you the final score on your continuous assessment. Okay, so that's for continuous assessment, which usually you will get it like week 14 or beginning of week 15. But of course, this round is a bit different. Then take-home exam. Take-home exam and case study report is actually two components that is actually replacing a final exam somehow. Okay, so we call it as alternative assessment. That's why you're actually having an online test on take-home exam, and also later on next week you actually have a case study report. For take-home exam cases, due to our last week, okay, I believe all of you are experiencing that, you including me, we can't access Spectrum in submission and so on. That's the reason why in the end of the day, I have shared a Google Drive link so that you are able, sorry, Google Form link, so that you are able to submit it through that particular form, and we are able to receive it successfully, right? So that's for take-home exam, the remarks. And the final one will be case study report. Case study report will actually start at Monday 9 a.m. You actually get your task. And as I mentioned previously, you're supposed to work in a group, and this group is supposed to be exactly the same with your project group. Okay, so whoever your members in, whoever that is actually under the same group project, okay, when you're doing in a group, right, then same group supposed to be applied for your case study report, okay, when you are doing your submission, and the leader will be the same as well, okay, because in the other day, if Spectrum still have issues, okay, I will actually create another Google form, but in that time, only the leader will need to submit the final report, okay. Case study report doesn't have any presentation, just the report itself. Okay. Sorry. So we move on to all the lecture notes. So eventually we have covered up all these 0, 1, 2, 3, 4, 5, 6 until 9. Okay. And now today we'll be going on to the lecture 10, non-parametric. So before I start, is there any question that you want to ask about the continuous assessment, including your quiz, midterm, and group project? Okay, as well as alternative assessment, including your take-home exam and also case study report. Anything else you want to ask? If you want, if you have any, then you unmute and you ask me now. 5, 4, 3, 2, 1. Okay, good. So right now, I hope everyone is quite clear what is happening. Hopefully there's no more students is asking me when is the case study report and so on, which is next week, and then you have 24 hours plus 12 hours of grace period. So your submission is Tuesday, 9 p.m. I've been repeating this like since last week, okay? So we move on to the non-parametric test, which some of you did extensively using it, but some of you didn't due to different kind of your report design, which is fine, okay? Because why? Non-parametric test is something that somehow not much more generalized, okay, compared to the parametric test. The first thing first over here, do you understand what's the meaning of parametric? Okay, you as a student, you should know, okay, translate is actually very important, right? Translate to your mother tongue language, then you roughly know what's the meaning. Parametric, oh, unfortunately, almost the same, but definition of parametric, relating or expressing terms of parameter or parameters. So eventually, parametric test is actually trying to tell you there are certain kind of data, okay? It's representable by using a number of parameters only. But non-parametric test is to cater on those kind of data that is actually not representable. It's actually quite fluctuate, doesn't follow certain kind of distribution. If you remember the word distribution, probability distribution, we still call in the class, we have like normal distribution, uniform distribution, and so on, okay? In statistical tests, we are actually having a strong assumption on all the data that we actually have is actually supposed to be following a normal distribution. If it's a continuous data, yeah, it's supposed to be following a continuous, normal distribution when your data size is actually big enough. Okay, so in that case, right, that's the reason why when you are doing a parametric test and your size, sample size is actually big enough, I'm actually suggesting to students is either you want to do the normality test, or you can actually skip the normality test and assume that the data is big enough to tell the distribution of your data collection is actually following a normal distribution. Because this is actually one kind of statistical assumption that we are actually following. But non-parametric test will be different, because non-parametric test is basically also called as distribution-free test. It doesn't follow certain kind of shape. Okay, parametric test, we are assuming the data follows a certain kind of shape, which is normal distribution. Okay, distribution-free, no. That's why it's also called as non-parametric test, because you can't really define a number of parameters and then you are able to draw the shape itself out. Okay. You remember when you are actually still recall your normal distribution, there's actually a certain kind of parameters that you can actually, a formula that you actually can derive from your normal distribution, and then you just need to key in the parameter of mean and variance. You are able to draw your normal distribution out. Okay, so only two parameters, then you are able to define your parametric distribution. Okay, so in that case, that's why it's considered as a parametric test, because your statistical test is following a parametric distribution point of view. Okay. So right now, the cause of the field assumption is the non-parametric tests are generally less powerful than their parametric counterparts. What does this sentence mean? If you look into the example over here, when the alternative is true, if your data that you actually collected, when the alternative hypothesis is true, means there are actually a difference. Sorry, when there are actually a difference, but when you are undergoing a statistical test, they may be less likely to reject the null hypothesis. Remember, null hypothesis is always equal, or there is no significant difference. Am I correct? If you follow this kind of idea, means in when your data collected or in a real life scenario, okay, if your real life scenario data is really showing that alternative hypothesis is true, okay, but if you are using non-parametric tests, okay, there is a possibility that there is a lower chance that your alternative hypothesis is actually accepted based on the data that you actually collected, because of the power is the power of the assumption. Sorry, the power of the test. Sorry, the power of the test itself is actually weaker. The power of the test itself is actually weaker compared to your parametric counterparts. Why is it true? So because imagine parametric test is actually quite straightforward. You have a shape, you follow, then you fit in the data. If your data doesn't really fit in, then okay, there's a significant difference. You have, you have two groups, right? Then you have two normal distribution, you just fit. If it doesn't fit, then you know that there's a significant difference. But distribution-free tests, you can have different kind of shapes. When you have different kind of shapes, right, even though there is actually a significant difference in real life scenario, but there's a very high chances that the small set of data that you're collecting, or the nature of the test itself to calculate the differences, is actually not able to show the differences enough. So in the end of the day, okay, the outcome is when there's a possibility, when both sets are normal distributions, okay, when you're doing parametric tests, you are able to reject your null hypothesis. But when you're doing your non-parametric test on the same set of normal distribution, there's a possibility that you will accept your null hypothesis. You wouldn't get exactly your expected outcome, okay, based on the data that you actually collected. That's also the reason why the assumption of normal distribution is actually applied at one point. Okay, so this is the meaning of so-called less powerful. Okay, given the same set of data, parametric tests will have a higher chance in rejecting the null hypothesis, giving you a meaningful outcome on your statistical research. Okay, comparing to the non-parametric test. Okay, of course, if you want to make sure that the parametric test is valid, you need to have a big enough sets of data. You need to make sure the data is actually really following normal distribution. These are the things that you need to fulfill. You need to make sure that your data doesn't have outliers like homogeneity or variance. If you still recall, some of you are actually applying on it. So these are the things. And then move on. So it should be noted that this test of normality can be subjected to low power. It's actually a little bit repeating. So data for distribution, low power is major issues. Okay. So this one, right, I already explained it, so you can read it by yourself. Okay. We look into the histogram form. Suppose there's a total of n equals to 20 participants in the trial. N equals to 20 is actually quite small. Yeah? And then randomize the experimental treatment of place pool and the outcome of data are distributed as shown in the figure below. So you notice that there's actually looks like this. The data doesn't seem appear to be normal distribution. That's why you need to use non-parametric tests. Maybe in this slide, right? There's actually one line is actually important. When the outcome is an ordinal variable or a rank. This is some of the students that is actually asking me at one point why we can use t-test on a Likert scale variable. Because when you are doing correlation analysis using Likert scale, for example, your continuous data coming from Likert scale from question 1, and then your independent variable is coming from the Likert scale from question 1, and your dependent variable is coming from Likert scale from variable 2. Okay, and then these two, you're doing a correlation analysis. Then when you are plotting your graph, even though it shows there's a significant difference, but your graph plotted outright, the line is actually quite weird, and your distribution of data is actually quite weird as well. It seems like the graph is meaningless to you, even though the test itself is actually coming out and tells you there's a significant difference. There's a correlation over there. Because why? When the data is actually ordinal, okay, it's not suitable to use a correlation test actually, and also even t-test and so on. It's just that for the class assignment purposes, I'm allowing you to do so because the nature of the data still are able to be considered as continuous data when we rip out the concept of ordinal at this point. Although Likert scale by default, it definitely must be ordinal data. That's the reason why when some of your groups that already done the presentation, I always highlight this one to you there. This is only for the assignment purposes that allows you to use t-test and ANOVA on the Likert scale version of data. Okay, because if you try to like come up with a statistical test, it looks fine, okay? And it's actually serve the purpose for your classes as to understand the nature of the data, okay? But if you are actually going into a real life scenario, Likert scale is actually doesn't make, it's not suitable for you to use a parametric test at all, okay? It's an ordinal outcome, ordinal data. That's why it's actually supposed to be using non-parametric tests, all right? So this is the first thing that I need to clarify, even though for the assignment wise, you are allowed to do so because I don't think I want you to redo your questionnaire and so on, right? But again, questionnaire is a way that to let you know that, okay, these are the things that you actually want to ask. So in for your project, then later on, how are you able to prove those concepts using these kind of questions? So right now, you know that, okay, maybe I will need to like improve the way that I'm actually doing the questionnaires and so on. So this basically serves as a learning process as well. Okay, so I don't really penalize you if you're actually having problems on your questionnaires, on using a suitable statistical test, because I know it's at one point it's actually difficult if you are not so understand about the nature of the statistical test, and then you go and do a questionnaire. But if I push the questionnaire timing to very like week 7 or week 8, I believe you have some difficulties in completing it in time. Okay, this is what I'm experiencing for the past 2 semesters as well. That's why I usually push the questionnaire much earlier than we actually allowed you to use Likert scale. But I will need to tell you, usually in this particular class, Likert scale is actually not so suitable at one point, right? We move on to the Mann-Whitney U test. We actually take only one test as an example here. There are a lot of other tests that is actually can be discussed in terms of how they calculate their statistics values. But we only focus on Mann-Whitney U, or another name is Wilkerson rank sum test. So this is actually a popular non-parametric test to compare outcomes between two independent groups. And if you still recall, the parametric counterpart is supposed to be t-test. Okay. And then let me see. Okay. See. So it's actually used to test whether the two samples are likely to derive from the same population which having the same shape. Okay. So you see, even though the parametric test of t-test, they are also measuring whether they have the same shape or not. Okay, or whether they are actually having close data. Okay, where the overlapping is actually high enough to show that there is actually a significant difference or not. But the shape that the t-test is calculated is always normal distribution. All right. But if you are using Mann-Whitney U test, any shape from the Mann-Whitney U test is actually acceptable. All right. And then some investigators interpret this test as comparing the medians between the two populations. Yes, because why? When you are using mean, okay, when you are using t-test and ANOVA, you notice that we are some of the material. If you did check online, you notice that the mean they are actually using the word comparing means. Even though SPSS, if we use it, is like comparing means as well. Okay, but you also remember when you are actually using means, it's actually affected by the outliers. If you still recall on your lecture 5 or lecture 6, right? And whenever there's actually one outlier that is actually very far away from your data, then the calculation of your means actually can be deviated, right? A lot. So in that case, right, whenever there's an outlier, it's not suitable for you to use the parametric test, because parametric test is based on mean. And that's also the reason why non-parametric tests can be used to deal with the data with outliers. And how do you detect whether they are outliers or not? If we are in lecture 6, okay, one of the way for you to detect outliers is you go and do your your box plot, okay, and then if it's like bigger or smaller than your 1.5 times interquartile range, okay, the equation I didn't recall it well right now, but roughly, when you're comparing the interquartile range, then you know which one is actually your outliers. But over here, we're actually having a test called homogeneity of variance test. Or some of you, when you are using your statistical test, you'll notice that it's actually called Levine test. Okay, so this Levine test basically will tell you that whether it's actually following homogeneity of variance or not. So when there's no significant difference, means that there's following homogeneity of variance means there's no outliers, right? So the original idea of Levine test basically is to help you whether there is to detect whether there's an outlier or not. But of course, in general term, when you are looking online materials, sometimes they've just mentioned, oh, your data is actually following homogeneity of variance, okay, or fulfilling homogeneity of variance. That's it. Okay, but the meaning behind basically is tells you there's no outliers. Because whatever data that you have, the variance itself doesn't have a very big difference, and at one point where the outlier is actually accessed. Okay, so why I'm actually highlighting all this is because to justify why they're using medians. Okay, because medians is actually, if you still recall in your week six class, I think median is actually robust when you are dealing with outliers. Okay. That's the biggest difference on medians, on non-parametric tests compared to parametric, because one use mean, another one use median. Okay. So basically, it's this one. This one is medians. This one is mean. So the null and two-sided research hypothesis for non-parametric tests are stated as follows: the populations are equal, the populations are not equal. Okay. So I also explained to some of the students that asked me, can we write null hypothesis on alternate hypothesis in this way? Which is yes. For your parametric test, you can also write in this way. So for example, if you want to write the students that the male students and female students that likes to study online is equal. Okay, so this one is null hypothesis. Then your alternative hypothesis, the male student and the female students that likes to study online are not equal. All right, it's actually equivalent to my example. There is no significant difference between different gender in terms of their preference on study online. Okay, it's also the same kind of way. So the wording maybe that you actually confuse is actually the word I'm using as significant difference, and also the word over here is actually using the word equal. Because you might say that, okay, significant difference means it's not exact difference, so you actually allow certain kind of grace amount of differences. But when we are writing this one, the two populations are equal, then we must make sure that the data from the mean or median is exactly equal. So in terms of the writing of the null hypothesis, right, we don't really go that strict on that part, because we know that we always define significance value for the statistical test to allow grace amount of differences to be accepted in your particular hypothesis. Okay, so in that case, when even you are using these kind of words that are equal, but you are not using the word like are significantly equal, it's also fine. Okay, that's why even though some of you, when you are writing in your hypothesis, there is no difference, I'm also okay, but I will suggest you to put in there is no significant difference, because the word significant here basically tells the significant value that you actually define, okay, in your statistical test. Okay, and that is the differences that you are actually allowing in your particular statistical test. Okay, well, if it's like more than this particular set differences, then you need to accept your null hypothesis in this case. If you check your descriptive statistics later on in your SPSS and so on, if you check your if you check your descriptive statistics on those tests that is actually having no significant difference, you will always notice the mean values, right, is actually not exactly the same. Okay, you always still having certain numbers of differences over there, but your outcome is actually trying to tell you there is no significant difference. Okay, so in that case, these differences that you are reporting from descriptive statistics, right, in terms of their mean value, is acceptable. The differences is not big enough for you to accept your alternative hypothesis, your expected outcome. All right, this how we are actually interpreting the data that we have. Then we move on to the assessment of normal distribution. This one, I think some of you are already doing very well in terms of using the test, but usually when you are presenting this part, I will ask you how you decide whether you are using Kolmogorov-Smirnov test or you are using Shapiro-Wilk test, because these are the two tests by default in your SPSS, if I remember correctly, because like all of you are using this one. So again, this one, I leave it to you to prove it to me, because I already hinted during the presentations for some groups, there's a way to choose, okay, which one is actually more suitable. So it's not that difficult to find out. So please go and find out if you are actually doing this extra, also optional task, if you are still recall my checklist, okay, for my tutorial groups, yeah. And basically this test is a goodness of fit test. Goodness of fit test basically tells you whether a certain kind of data follows certain kind of shapes or distribution or not. That's why it's using the word goodness of fit. And Kolmogorov-Smirnov, Anderson-Darling, and Shapiro-Wilk basically are the among of the normal distribution tests. Okay. But when your H0 and H1 is almost the same, okay? This one follow a normal distribution. This one does not follow. So this one is equal. This one means equal. This one means not equal. Okay. Okay, we move on. Data that does not fit a known or well understood distribution is referred to as non-parametric data. So data could be non-parametric for many reasons, such as this one is ordinal, interval, and other form, real value, but not understood shape. You see, ordinal but not well understood shape. Sorry, and also contains outliers. So all this, right? You notice that when the slide goes on, right? You notice there are some content that's actually repeating, but it's actually referring to the same thing. All right. And most parametric have a non-parametric version. Less powerful is the same thing. So this one is a summary. It's the same thing again. Since non-parametric do not estimate the population parameters, in general, there are no estimates of variance, no confidence intervals, fewer measure on the effect size. Okay, this one is just some characteristic that you might want to know. This is the thing that important table that you're supposed to look into. Parametrics must follow normal distribution. Non-parametric and distribution is fine. Assume variance, homogeneous. Non-parametric doesn't really assume variance, so it's any. So any means that it can be heterogeneous, means there is actually outliers. Okay, some of it having outliers, some of it doesn't have, or even you don't have outliers, you still can use parametric. Okay, so remember this word any basically tells you that if it's following a normal distribution, you can use parametric, you can use non-parametric. Okay, but if it's not following normal distribution, then you must use non-parametric. All right. And this two is like an N kind of situation, means that these two must follow. These two must follow, must fulfill in order for you to use the parametric test. Then we move on to the typical data, ratio interval, and this one is ordinal and nominal. So you notice non-parametric sometimes is more on nominal data, okay, grouping data, and then parametric is more on continuous data. That's why you have ratio and interval. Then we have data set relationships, independent, and then any. You assume that the data is actually independent, you don't affect each other. But non-parametric test, if you still recall, it can have a I think what some of your friends asked me about a chi-square independent test. This is actually for you to test whether it's independent or having relationship or not. Okay, this is the main thing that we have explained just now. Mid-parametric using mean values, non-parametric is using median values. Okay, but benefits of it is that can draw more conclusions. Simplicity is for non-parametric is actually more simple and less affected by outliers. Okay, but again, we still, at one point for statisticians, parametric is much more useful, and in their point of view, as long as they make sure that their data collections actually able to follow normal distribution and homogeneous. Okay, by collecting as much data as they can. Then the test that we are having for parametric and non-parametric counterpart is actually this one, like correlation test. For parametric, you have Pearson versus Spearman. T-test for two groups independent measures. You have independent measure T-test or independent sample T-test, or I think it's two independent sample T-test. There are a lot of different names. Okay. And then you have Mann-Whitney test or Mann-Whitney U test or Will-Subcon, if you still recall. Okay, and then you have this one-way ANOVA. This one is Crusoe-Wallace. This one is match pair t-test, but in my previous slide, I think it's called pair t-test only, but it's the same thing. And this one is Wilcoxon, sorry. I think this Mann-Whitney is having a different name, right? Wilcoxon rank sum. Okay, this one is Wilcoxon rank sum. This one is just Wilcoxon itself. It's a bit different. Then this one is repeated measure, two conditions. More than two conditions. This one is repeated measures ANOVA, fragment test. So repeated measure ANOVA, some of you ask me whether it can be used for your data that is actually having checkboxes outcome, where a respondent can actually take multiple of it. I think I directed a website, okay, to the students. So if you're interested to know more, please go and check. It's not that difficult to find out. You just need to Google repeated measures ANOVA, I believe. Then you'll be able to direct it to a sheet to explain exactly what the repeated measures ANOVA is. But not suitable. Okay, what I can tell is not suitable for you to use in your checkbox data. Okay. So in order for you to do your checkbox data, the suggestion is every single checkbox you need to convert to become yes/no answer. Okay. Then move on. Before a non-parametric statistical method can be applied, the data must be converted into a rank format. Okay, this is the part that you need to understand more. What do we mean by rank format over here? Okay, or in order for you to perform your non-parametric test, okay, you need to change the data values from the exact value itself to a set of ranks. Okay, so a statistical method can expect data in rank format, sometimes called rank statistics, such as rank correlation, rank statistical hypothesis test. Yeah. So it's the same thing. Just talking about correlation. So you have Spearman and Kendall correlation. Compare sample means you can use Friedman, Mann-Whitney U, and Wilson consign rank test. Okay. This one is the Mann-Whitney U that we're actually focusing. Non-parametric alternative test to the independent sample, t-test, for two independent groups. When the assumption of the t-tests are not met, you can use Mann-Whitney U. Results are presented in group rank differences. Then you are actually having a set of characteristics to follow, including a dependent variable should be measured at the ordinal or the continuous level. So that's why remember the ordinal data that you have in your Likert scale, then it's actually suitable to use Mann-Whitney U, given that your grouping variable is two groups. Okay, it must be in two groups, and the data is not normally distributed. Okay, this is the equation actually that you need to follow. If you directly see the equation, then you start to feel blur, but we move on. Then we only come back to the equation. So the theoretical concept here is from 0, complete separation, to n1 times n2. You want to make sure that it's actually most likely false for your, sorry, he's talking about range of U. So when you're actually talking about a range of U, it's actually ranging from 0 to 25. Sorry, 25 is over here, right? Yeah, 25 is over here. That's why it's actually better for me to explain based on the example. So anyway, we somehow skip that part, this part first. Although there's something that you actually can follow over here, we move on the concept. Oh, these two are the same. Oh, because why is actually when I'm using a PDF as a presentation, then these two will be like transition. Okay, we start with this one. Okay, before we go into the equation, so that you have some idea what the equation is actually about. So we start over here, yeah. Okay, prepare for like another 5 seconds. Take a look on this one first before I explain. Okay, a company wants to investigate the effectiveness of a new causes for running system tests to reduce amount of time or hours for test execution. So this one is the background. So a total of n equals to 10 participants are randomized to attend either the new courses or the existing course. You actually have two things over here. They have existing course, you have new course. And participants is asked to record the amount of time taken. The amount of time taken to execute the test over a 1 week period following receipt of the assigned course. So the data are shown below. So some of them is actually using 7 minutes, 5 minutes, 6 minutes, 4, and 12. Some of them is actually 3, 6, 4, 2, 1. So is there a difference in the amount of time for test execution over a period of 1 week for those participants who attended to the new course compared to those who attended the existing course? So notice that you are actually doing a two groups analysis because you have existing course and new course in terms of the time taken, okay, for them to execute the test. So if it's just a rough view from here, you might feel that existing course is actually having much longer time compared to new courses, or it's actually just a perception point of view. So again, for us to prove this one to be true, we will need to undergo a non-parametric test because your sample size is actually quite small. We can't really assume normal distribution from here. So in that case, small sample size, significance level 5%, N1 equals to N2 equals to 5. What do we mean by N1 and N2 here? Group 1 and Group 2. Okay, and N basically is number of samples. Number of sample size for Group 1 and number of sample size of Group 2 is actually equals to 5. Because you have 10 in total, you divide equally into two groups. Then you state the hypothesis. The two populations are equal, and then the two populations are not equal. Of course, in here, right, you notice that the hypothesis is actually quite straightforward. But I would strongly not suggest you to do these kind of straightforward hypothesis in your assignment. Please make sure that your independent and variable and dependent variable is clear, because This one, because we are explaining continuously, so we know that this population that we are referring to basically is referring to the populations of existing costs and the new costs. And we know the dependent variable is actually the time taken. That those things supposed to be inside here actually. Okay? Then we move on. This is the part that you might want to take some time to understand. Remember, this is actually the data that we have originally. Can you see my mouse at one point? You can see my mouse moving, right? Can you?
Yes.
Okay, good. All right. Can we move on? Let me move back. Okay. So when you see this part, it's actually identical to this part. Okay, we just bring the data over from here to here. Then we actually we need to do a process of reorganize the data first. Reorganize, or you basically use the word sort. You sort the data from smallest to largest first. So from this part to this part, ordered a sample smallest to largest. So that's the reason why when you are actually reorganizing it, this one will become 1, 2, 3, 4, 6. This one will become 4, 5, 6, 7, 12. But because you want to order it in terms of existing costs and new costs in the same set, okay, that's the reason why when you're actually reorganizing this one over here, this is the smallest, it's become the first one. 2 is the second smallest, it become the second one. 3 is the third smallest, that's why it's the third one. 4, both places have 4, so both places you put in 4 over here. Then you have 5, 6, both places, then 7, then 12. Notice that this one is your original data. This one is your newly calculated data, newly ranked data, but it's actually having 2 sets combined together. Okay, it's just that you are writing in a different column, but it's actually combined together at one point. Okay. So then you have new courses over here. New courses is the same. You rearrange it, then you become 1, 2, 3, 4, 5, 1, 2, 3, 4, 6. So right now, from here, you move on to the ranks that you have. Okay, the rank is actually using the integer concept. Okay, that's why if you have 10 sets of data, it's supposed to become 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, if we right now when we are assigning the ranks, okay, you notice that the first one, okay, the first one, second, third, fourth, you have 2 to share. Okay, so basically 4 and 5 is here. Then only you move on to the 6 values. But 4 and 5, you can't really know that which one is having a heavier load, right? That's why you divide it. 4 plus 5, 9. Divide by 2, 4.5. That's why both of it you are assigning 4.5. Okay. Then you actually have 7 and 8. Both are actually have at this particular sharing by this integer 6. So in that case, 7 and 8 plus together divide by 2. Both of them is assigned 7.5 rank. Then this is a 9 rank. This is a 10 rank. Okay. So this is how you are converting from your original data. Okay, this one is your original data in terms of values. This one is actually in terms of rank. Okay, when you are actually having like 10 points of data, then you have 10 ranks. Then you have 100 points of data, then you have 100 ranks. Okay, so from here, you'll be able to summarize this one existing cost. You sum based on columns. This part is actually considered RI. Okay, RI, and this one. Sorry, ranks. R is ranks, right? Sum of ranks become R1. This one is becoming R2, assuming existing cost is 1, new cost is 2. Okay. Then we move on. So you know that existing cost, the sum of ranks is 37, new cost, sum of ranks is 18. The sum of ranks will be always equals to this one of the chunking that you actually need to do. The sum of ranks will be always equal to n bracket n plus 1 divided by 2. Okay, so when you actually check on the assignment of the ranks, we have n plus 1, which is 10. Okay, n is actually, okay, in here you're supposed to use a bigger n because it's total n. Total n equals to 10. Then 10 plus 1, which is 11. That's why you have 10 times 11 divided by 2. You got it 55. And you'll also notice that 37 plus 18 is 55. Okay, this one is actually checking on your rank values. Okay, then we move on. Manual calculations. You are now calculating U1 and U2. Okay, U1 and U2 are actually following this formula. Remember, right now we are actually referring one is existing cost, group 2 is new cost. Okay, so N1 times N2 is actually the same. You're actually having 5 times 5. Remember, just now your N is actually the sample size for group 1. So M1 is sample size for group 1, N2 is sample size for group 2. And this one, again, sample size of group 1, sample size of group 1, sample size of group 2, sample size of group 2. And this one is actually your sum of ranks. If you still recall, it's coming from this table. So this table basically helping you to convert your data into ranks, and you are able to calculate sum of ranks. If you are able to do the chi-square calculation by yourself, right, next time if you are interested and you go and study yourself, it's also similar cases, okay? I mean, not exactly the same, but if you are interested, you can go and find out the manual way for you to calculate different kind of non-parametric tests, okay? But here we are actually giving you one example. Then that's the reason why you will be able to get these kind of outcome. Okay, U1, when you're replacing the data inside, you have 5 over here, sample size, and this one is actually your sample size as well. When you sum it out and you minus your rank that you actually have previously, then you got 3. This one, same cases when you're doing it and then you minus it, then you'll get 22. This is the part where you want to double check as well whether your calculation is correct or not, because this and this, when you sum together, equals to N1 times N2. So these ones is summing up together is 25. These two times together is also 25. So your calculation is actually correct. Where does it come from? This is where the key concept over here. The theoretical range of U is from 0 to N1 times N2. All right. Complete separation, that's why it's like complete separation between groups most likely false and HA most likely true. When you are getting lower and lower values, okay, HA is most likely true. Okay, when you are getting higher and higher value, okay, very little evidence to support HA means you're accepting your null hypothesis. So in here, this key concept is trying to tell you when your U value is very high, okay, U value is very high, you accept your null hypothesis. When your U value is very low, until a certain kind of values that you need to compare, then you reject your null hypothesis, accept your alternative hypothesis. It's actually quite similar to the concept of your SPSS scale test. It's just that this time you doesn't know the critical value yet. In your SPSS, you always refer to sigma value, which is 0.05. Right. In here, if you are calculating the U statistics, you still don't know what is the critical value yet. All right. Then smaller values of U support research hypothesis. Right? But how small? How small you doesn't know. So that's why we will need to find out what is the critical U. Okay. You have calculated U, which is U1 and U2 that you have just now. But you also need to compare with your critical U. Where this critical U comes from. Okay. Unfortunately, we didn't put definition in front, so that's why you are having issues of understanding it. But when you are explaining the things behind, you know the whole concept of calculating, then you can roughly get the meaning of U over here. Okay. So once you get this right, okay, you have U1 and U2. You need to decide what is actually your calculated U. Okay. So calculated U and U values is coming from when you actually calculate deciding to calculate values, right? If you have U1, U2, you pick the smaller one. All right. Remember this Mann-Whitney U test, you only have 2 groups, so you don't have U3, U4, and U5, and so on. So U1 and U2, when you compare which one is smaller, it will be picked as your calculated U. Okay. So right now, based on U1 and U2, U1 is actually smaller. That's why this one is your calculated U. Okay. Remember that one first. Your calculated U is 3. Calculated U is 3. Then you have critical U value for N1 equals to 5, N2 equals to 5, and your significance values is 0.05 is actually 2. All right. So in that case, you will be able to see over here. N1 is here. Okay. So it's actually this column. N2 is here. Is this column. So basically it's either 2 or 0. And you are actually setting your sigma value to become 0.05. Sorry, your significance value to be 0.05. Then your critical U is actually 2. All right? Repeat again, critical U value is actually 2 because of this one. I can't really click, but it's actually this one. Okay? Move on. So right now, when you're comparing it, calculated U is actually bigger than your critical U. That's why 3 is actually bigger than 2, right? So you do not reject the null hypothesis because your critical U, because the calculated U is bigger than your critical U. Okay, when you are comparing with your threshold, the threshold can be your critical U, can be your 0.05 and so on. When it's bigger, means you basically accept your null hypothesis, you reject your alternative. Okay, so you don't really have enough statistical significant evidence to show the two populations of amount of time over a period of 1 week is not equal. So this one is actually just to tell you that you don't have sufficient proof to tell it's not equal. That's why your statistical test outcome is both of the sets are equal based on these sets of data, which you feel is actually supposed to be different. But don't forget that there's actually a number of overlapping. You see, this one is overlapping, this one is overlapping. Although you can see the maximum and minimum value is actually quite far away, but it's still not enough for you to tell because maybe it's actually an outliers and so on. Because you see 4, 5, 6, 7 is almost the same, but it's suddenly having a 12. This can be an outliers. All right. So in that case, it's strongly suggested for you to, like, for example, collecting more data for you to do a parametric test, for example, or you are actually, if it's just based on this 10 sets of data, then it's really no significant difference. Maybe this one is really an outlier itself. Because if you look into this one comparing to 4, 5, 6, 7, doesn't really have a big difference. This is how they deal with outliers itself. Okay, because you see, once you converted it to rank, right, the effect of 12 no longer there. Right? You notice that it's like the whole thing is like flattened. This thing, when you're calculating it, is actually whole things are flat. You don't really like affected by the sudden change of values from 7 to 12 at this point. Okay, so hopefully you can see the difference. So if you go into Mann-Whitney U test, you're actually able to see the two non-parametric tests, 2 independent sample. You are able to put the group values, define groups, then you are able to get your outcome. And this is the reason why do not reject null hypothesis. Maybe some of you will ask me why we don't use asymptotic sigma. But when because there are some tests you only have asymptotic sigma, but because if you follow asymptotic sigma, there is actually a significant difference. So you see that. But you see, asymptotic p-value is appropriate for large samples. Okay, exact p-values is independent from sample size. So usually when we have the choice, we will actually use the exact sigma, okay, or p-value. But if you have no choice, then you need to use this asymptotic sigma. All right. So in that case, it's actually quite close to rejecting the null hypothesis, but it's still not enough. All right. So this is how you get the Mann-Whitney U to have 3 as well. So basically, the SPSS, right, skip you the difficulty on this one. You don't need to memorize, or you don't need to double check this particular table again for every single critical value that is actually different, because they will actually calculate you sigma value that you always need to remember always is 0.05. Then that's it. It's actually derived from your Mann-Whitney U. If you want to know how to derive it, you can check the SPSS how they do it. All right. So Mann-Whitney U practice. I think you can actually download this one. Is it? Hopefully they are. I think it's coming from here. If it's not right, please let me know. If I recall correctly, I think it's coming from here. Right. Then you'll be able to do the same calculations, and that's it. All right, so this is the example for Mann-Whitney U. Actually, if you notice that if you follow back to your ANOVA explanation, if you recall every single table coming from your mean square value, is it? Mean square value, and then your degree of freedoms, and then other calculations and so on, if you still recall the table, okay, if you still recall the table itself, this is actually a step of process for you to calculate all the F statistics, for example, for ANOVA, then T statistics for t-test, and then this one is for U statistics. So there are many ways. So we don't really tell you every single one, but if you're interested, you can go and find out. But in general, all these tests can be executed by SPSS. The important thing, for example, in your group project is you need to make sure that the way that you are you explaining and applying your SPSS statistical test is actually valid. Okay, so that's all from the non-parametric. Let's see whether there are questions or not. No questions. No questions from the floor. Any questions from the floor before I move on quickly to the tutorial? It's like a 1 hour class already. Okay, so far so good. Hopefully so far so good. Since no questions, we move on to this one. So this one, right, I will actually not spend a lot of time on this one because this one is actually can be another, you see there are 7 chapters inside here. It can be like another few hours of classes. Okay, so it's actually based on your own effort, okay, or own initiative, whether how far away you want to investigate on it. Okay, even if you don't investigate this part at all for this particular tutorial, right, I believe you still be able to complete your group project. It's just that you always need to assume your data to be normal, okay, and also following homogeneity of variance. But it's actually good for you to know what this is about, okay? It's actually another whole process again to explain to you what is a parametric and what is a non-parametric and which one is not powerful and so on. It's the same thing, okay? At one point, the explanation is the same thing, and then this one I'm actually adopting from here, so you don't need to repeat it again at one point. And then the good thing about here is it's actually showing you step by step. How are you able to get the data, analyze it, non-parametric test using a chi-square, and so on. So if you are facing difficulty in using non-parametric test, right, you can actually use this example over here. What you need to do here, what you need to do beforehand is just to identify which one is suitable for your cases. Okay, that's why all the SAV files is already put inside, I believe. So you can try yourself if you are interested. Yeah. Okay. So yeah, again, as I mentioned to you, I will not go through very detailed. Okay, not even I will not even explain explicitly for every single test that you have, but maybe from the table of contents, what you want to look into it. Maybe if you want to double check chapter 1, which can be like very similar to what we have in the class just now, then you might want to take a look like maybe chi-square, Kolmogorov-Smirnov, Mann-Whitney U. What else? Kruskal-Wallis, Wilson-Consign ranks, and maybe Fredman as well. Yeah. But the other things is actually useful as well. It's not to say that it's actually not related, because this whole part of your non-parametric is actually much more comprehensive, but we are actually doing an introductory part of it, so that's why you don't really see us go through very detailed. Okay, because even though it's actually quite a lot from here, it's like 20 or 30 pages, not slides here. Okay, so yeah, you can take a look on this one if you're interested. Okay. Let me see there are questions or not. Why we are not focusing too much on non-parametric? Because this is something that you should know. But even though you didn't do it for this particular courses, we lecturers still feel that it's okay. But please bear in mind that there is actually something that you need to make sure before you're doing parametric tests, and there's a counterpart of it that can always apply to different kind of shapes and so on. But the prediction power of what we call as a, we should not say the prediction because it doesn't do any prediction, but the statistical significance, okay, on the non-parametric test is actually not that strong. okay, compared to the parametric one. The outcome that you are actually can be deduced from here is not as powerful as parametric test. Okay. So any questions from the floor? It's like already 1 hour. Any questions? If no questions, then I move on to the group project questions. Do you have any group project questions you want to ask? In general first, before I ask the group leaders. Hello? No questions? Everyone are doing very well in their group projects? Make sure you can complete it in time. Okay, no questions. No response somehow. 81 of you right now. Okay. Okay. So some of you are asking me maybe the case study report. Okay, whether the case study report is actually only lecture 7, 8, 9, 10, and then lecture 1 to 6 doesn't have it anymore. What I can tell you is it will be related somehow because again the concept is coming from the lecture 1 to 6. I will not ask you questions like similar to question 1 to 6 where you need to solve some equation and so on, but the concepts coming from there, like the distribution concepts, okay, probability distribution concepts, and also the things that you learn from lecture 6. Lecture 6, including your concept of mean and median, how you actually decide, okay, sorry, how you actually do your parametric test in terms of mean and also do your non-parametric test in terms of median, okay? Why they are in the other day using mean and median as their central tendency measure rather than other ways, okay? Why at one point parametric test must assume normal distribution, must assume homogeneity or variance, must understand the reasoning behind, okay, rather than you just simply applying it, okay? Okay, if there's no questions, then I'll be ending the lecture. Basically, this is the last lecture that we have before we have the case study report next week. So I move on to call upon all the different group leaders, okay, in my tutorial group 1 and 2. So tutorial group 6 and 7 students, if you want to leave, you can leave now. And eventually I will stop the recording at this point. So last call, any questions? Last call. It's like in a cafe and we are having last call right now. If no questions, then I will stop the recording. And that's all for today. Please stay for your tutorial 1 and tutorial group leaders. Tutorial group 1 and group 2 group project leaders. Okay, please stay for a while. And yeah, okay, I'm stopping the recording and stopping the screen share as well. Thank you. Okay, so I will call one by one for the group leader. Basically, I'm following the sequence. So let me see. I don't think I can share the team screen. Can I share the team screen? Let me see.